Hello, I'm James Floyd. Today we're going to be doing some problems from Chapter 30, Module 1 on induction and inductance. So here are a few highlights from that chapter. Say if you have a B-fill piercing a flat sheet. We're only going to have the component perpendicular to the sheet. Now here we have the B-fill coming this way. It's only going to pick off this component perpendicular to the sheet. Now we have the formula phi is equal to the integral B dot dA. In this case, where we're perpendicular to the sheet, we can just write phi equals BA when we're solving our problems. In this case, where we're not, we're going to have to do the integral. Here's an example. The magnetic motion creates a magnetic dipole that opposes the motion. We're bringing this rod toward this ring, and we have mu. This is going to be the opposition. Mu is equal to number of turns, current, times the area of this ring. Lenz's law states as the magnet is moved toward the loop, a current is induced in the loop. The current produces its own magnetic field with magnetic dipole mu orientated so as to oppose the motion of the magnet. Thus, here's an example where we move the magnet toward the loop and we produce a amperage in this loop. If we move it away, the current will flow in the opposite direction. So we can create a current by moving the rod in and out of the ring, or the relative motion. We could hold the rod still and move the ring back and forth with the rod stationary. So we have, let's start with the first problem. Problem 6. This figure 30-37A shows a circuit consisting of an ideal battery with EMF 6.0 microvolts, a resistance R, and a small wire loop of area 5.0 centimeters squared. For the time interval T, 10 seconds, 20 seconds to 30 seconds, the external magnetic field is set up throughout the wire. The field is uniform, its direction is into the page, and the field magnitude is given by B equals AT, where B is in Teslas, A is a constant, and T is in seconds. Figure 30-37B gives the current I in the circuit before, during, and after the external field is set up. The vertical axis scale is set up by IS 2.0 milliamps. Find the constant A in the equation for the field magnitude. We see that IS is 2.0 milliamp at this point. So here, the slope where we're beginning is 1.5 milliamp. Now the battery has E of 6.00 microvolts. So we know that R is equal to E, yes, is equal to E over I. So when we divide 6.0 times 10 to the minus 6 volts by 1.5 times 10 to the minus 3 amps, we get, okay, when we divide 6.0 times 10 shift to the minus 3, this minus 3 goes up as a plus 10 to the third, divided by 1.5, we get 0.004 ohms. So we're going to use this to see if we can find the EMF in this coil. We know that the battery is 6.00 microvolts. So we can say battery 6.0 times 10 to the minus 6 volts plus the EMF that we desire, that we don't know, divided by R, which we do know, 0.004, is equal to current. We can get the current off of the graph. And at this point is equal to 0.0005. So we'll multiply this 0.00 times 5. We'll do this. 6.0 times 10 to the minus 6 volts plus the EMF we're looking for is going to equal to 0.0005 times 0.004. When you do the math, E is going to equal 0.0005 times 0.004 minus 6.0 times 10 to the minus 6 volts. So let's see, voltage here is going to equal 2 times 10 to the minus 6 volts minus 6.0 times 10 to the minus 6 volt is going to equal minus 4.0 times 10 to the minus 6 volts. Okay, just to be clear of what we just did, we solved for R first. We used the fact that we knew the voltage in the battery and the current that we got off of our graph here at this point is 1.5 milliamps. And then we said, well, then we set up Ohm's law. We said that the total voltage, which would be the voltage from the battery, plus the voltage from the ring that we don't know, from our induced current, divided by R, would give us 0.0005 amps. And then we solve for E, the voltage. and we came up with E is going to equal to minus 4.0 times 10 to the minus 6 volts. So let's write out a formula for E induced. We're going to have E is equal to d phi over dt. And this is going to equal to d b times a over dt, which is equal a dB over dt. From here, we can see that, going back to our problem, it says that B is equal to AT. So we can see here that A, looking at this, is equal to B over T. So this dB dt is A. So we'll have equal A times A, the constant that we're looking for. And we know what E is. So when we solve, and we know what A is, the area of the small ring. So when we solve, we're going to have A, get this out of the way, is equal to the inductance E over the area, which equals to 4.0 times 10 to the minus 6 volts divided by 5.0 times 10 to the minus 4 meters, and this is equal to 0.0080 Tesla seconds. So that's what A is equal to. That's what we're looking for. Thank you.